Okay, particle physics, here we go. I do have two extra videos that are not by me, by someone who's, just a tiny bit more than I do about it, Brian Cox, that I'll expect you to watch and have some understanding from as well. But here's my little go at it that matches your notes. Oopsie, sorry. So the standard model, if you ever hear that term, basically means that they've sort of broken down all the atoms, or not the atoms, all the particles that they believe exist, like the very smallest particles. And most of them have been found in particle colliders. The idea being that, we learn about, well, one time they thought the atom was the smallest particle, right? And I think you would have studied that in chemistry. And sort of as time's gone on, they've realized, okay, no, the atom is definitely made up of the nucleus, which is protons and neutrons, and electrons. And what physicists have done since then is they've tried to break those particles up into smaller bits of matter, and they've been successful. Not with the electron, but this idea of a standard model is just a list of all the, what they call, like, the fundamental building blocks of matter. You hear that term with physicists all the time. And that means that smaller than the atom, smaller than protons, not smaller than the electron. The electron is one of the smallest bits. And one of the ways that they test that, the easiest way, is they take two bits of matter, say two protons, and they get them going really fast, and they make them run into each other. And as most things do when they run it, when they have a big collision, is they break apart. And then they discovered these things called quarks that make up protons. And that's basically it. And then there's these electrons, and electrons, they haven't break up into anything smaller. But these are sort of a list of all the particles that they think are the very smallest. And a couple of years ago, they had this big deal about this thing called a Higgs particle, which mathematically had to exist for everything to exist. And they found that after 1969, a physicist named Peter Higgs predicted its existence, but they could never find it. And that's why that's one of the main reasons they built that huge particle accelerator in France and Switzerland, I think, it crosses the border, and they found this Higgs boson there, which is kind of exciting for them. But again, Brian Cox has a nice explanation of all that. So what you need to know are things like, what are the main, what we call matter particles that stuff is made out of, right? We are made up of quarks and leptons. We know we're made up of atoms, but those atoms are made up of protons and neutrons and electrons. Electron is a lepton, and quarks are what are used to make neutrons and protons. So that's 12 of the different particles that exist. And what they've found in laboratories, like, they find some of these particles only they only exist for a very short bit of time, and they'll decay and become another type of particle, right? They can see it. And so it's kind of neat, because the way that these particle physicists work is they use math. The theoretical physicist, that's the Sheldon, I don't know Sheldon's last name, but Sheldon from Big Bang Theory. He'd be the theoretical physicist, right? And he would do all this math, and he would predict the existence of a certain type of particle. For example, say the Higgs, but it doesn't have to be the Higgs. It could be any of these. I know, like, when they found these neutrinos. So mathematically, they thought, okay, this particle must exist. And then the experimental physicists, which is the Leonards of the world, they take the information from the theoretical physicist, and they try to create conditions in a lab in order to make that particle. And usually, with these standard model, it means decaying other particles to become that, right? And that's essentially what physicists do. There's theoretical physicists who mathematically come up with ideas, and then there's the experimental physicists who actually figure out how to make that actually happen. And that's what goes on in these huge particle accelerators. But anyway, a lot of the particles that they've predicted mathematically should exist, like theoretically should exist, they have a hard time finding them. But I think all the ones, the Higgs was the last one, and it took them 69 to about, I guess that'd be 40 something years. Is that right? 69 to 99 would be 30. Yeah, 40 something years to actually to prove its existence. So, of those basic particles, then quarks, there's, I think, is there 6 quarks. So a proton is made up of 3 different quarks. And you know how a proton has a positive charge, a positive 1 charge. Well, you know, a quark each has 2/3 charge, and then, and so they have, they have 2 quarks that are each 2/3 up quarks, and then a down quark, which is a minus charge, and they join together to make the 1.6 times 10 to the negative 19, in which it is. Okay. Leptons, on the other hand, they're smaller than quarks. So quarks make up the neutrons and the protons. Leptons are the electron, but plus a bunch of other types of particles that exist only on their own. Like they're not part of the atom specifically. Not like protons and electrons are. And they're either -1 charge or they have no charge. So they can be categorized by generations. So if you look at a table of, these are called matter particles, right? So these are the quarks, up, like the names, up, charm, top, bottom, strange, down, I don't know. And then you don't need to memorize those names by any means. The leptons, you know, they have the 3 types of neutrinos. You might remember a couple of years ago, there's all this talk about getting neutrinos to travel faster than the speed of light, but then they found that it wasn't practical, wasn't happening. Neutrinos are itty-bitty though. They're almost massless. They have even less mass than an electron. And they say that neutrinos sort of pass through us all the time. Like we can't, they're almost unobservable. They're very difficult to observe. But anyways, what they say is that these particles that follow in this row, they'll call them generation 1. They're the most stable, and they're the ones we see the most often. These are the really unstable ones, right? And so they hardly ever find them, have a hard time finding them. Yes, neutrinos have very low mass and no charge. And this is, don't worry about this picture very much, except for that's kind of cool. Like when they first started doing particle collisions in order to see what they could make, this is what they would study. It was very manual, right, in 1970. Now it's all electronic, of course, and much more visible. But what these represent is there must have been some collision with a proton right here, and so they would have tried to do this, collide a proton with what they thought would be a neutrino, or with another particle, sorry. And they created a different type of particle because neutrino disappeared right away, and so they couldn't detect the neutrino because it's got no charge, it's got almost no mass. But what they could do is they could say, well, this proton, right, it came out with these 2 particles afterwards. And so they deduced the location and the fact that the neutrino even existed. So these 3 lines represent things they could measure, but they can't measure anything with the neutrino. But they just know from sort of deduction that it must have been there. So, or inference, I guess. So just to give an idea, if you had a neutron, for example, a neutron might decay into an electron and a proton, right? And they can watch, and they detect a neutron. They can detect the electron and proton disappearing when the neutron decays. But if they're both moving in this direction, conservation of momentum says there must have been something going over there, and that it's something that they can't detect. And that's more or less what I was trying to explain against the bubble page there, right? They can detect that there must have been something there because of looking at just simple conservation of momentum, just like you and I could do, right? And so that's how they figure that it's there. Not because they can directly observe it, but something. If this neutrino is sitting still right here, right, and then an electron and proton take off in this direction, something must be going the other way. Okay, so that's neutrinos, very light, no charge, hard to detect, and it's this neat idea of what particle physicists do, which is they infer things. They may not see it, but they can guess that it must be there. And then there's this idea of antimatter, which is a whole other type of matter, and it's like the It's like the evil twin. The electron has an evil twin, which is the same, exact same in every way except for charge, because a positive electron is the same mass as an electron. It's called a positron. It just has a charge of 1.6 times 10 to the negative 19. It's not very prevalent. Like, positrons aren't around very much. No antimatter is. But they're identical to every other particle that exists, and they've all been observed, all these antimatter particles. And when antimatter and matter get together, it'd be another way of generating a whole crap load of energy, because they annihilate each other. So then all their mass turns to energy. If you could control that, or if you could have enough antimatter to make it happen, it's just not, it's pretty unpractical right now. Though from a theoretical point of view, it makes sense. You can make tons of energy. However, antimatter is pretty hard to come by, which is a whole interesting idea. Like, lots of physicists ask, well, why is it? Like, why do we have so many of what we call matter particles? Like, why so many electrons and so few positrons? Why wouldn't they be equal? Why wouldn't that be balanced, right? Okay, so another type, so there's the matter particles, there's the antimatter particles, and there's these things called bosons. And there are 4 different particles of which the graviton has not been observed. They have no evidence of it. But there's actually 2, I guess, with the weak force. But there's the gluon, the photon, which we've talked about before, and these things called the W and Z bosons. And then there's this hopeful thing called a graviton. But the idea is that, okay, well, how does force work? Like, how is it that electromagnetism actually works? Like, we just trust that it does. And the basic idea, and like I say, Brian Cox does a better job explaining it, of course, and that's why his video is so good. But the basic idea is that, you know, 2 charged particles, if they exchange a photon, one photon goes from, say they're 2 particles of the same charge, and they're moving towards each other. They predict that what happens is one particle will emit a photon and bump the other one. And that'll give them, based on conservation of momentum, they'll both move backwards because they're repelling each other. And it's this exchange of photons that causes the force that we observe. A photon moves from one to the other, they repel each other. It looks like, you know, there's some magical force causing them to repel, which kind of is true, but it's actually just a photon. And a gluon is the particle that's associated with a strong force. And the strong force, again, is the force that holds the nucleus together, keeping in mind that you'd think inside a nucleus, why do those protons stick together? They're all positive. Why don't they repel each other? And they call it the gluon particle that keeps them together, or the strong force, which is, gluon is the carrier particle for the strong force. The weak force, again, is the force that causes things to decay, radioactively decay, and then that's thought to be caused, or not thought to, but witnessed, evidence says that it's these 2 particles they call the W and the Z that cause that to happen. And then there's the graviton, which has not been observed. And so we don't know if gravity, physicists don't know if gravity, they don't understand it very well. They can predict it mathematically using Einstein's equations, but they don't really get why it happens. And they, you know, almost for the point of view of what they call symmetry, that, you know, there's they've observed all these other particles causing the other types of forces. You know, a lot of physicists really believe that there must be a graviton, a carrier particle for gravity. And one hypothesis is that the graviton particle, it actually, you know, the reason they can't observe it is also the reason why gravity is so weak. And they think that the graviton, there's a guess, it's not, I think is a strong word, there's a guess that gravitons might slip from one dimension, from our dimension, to other dimensions. And when they slip to other dimensions, we can't observe them anymore. But that would also explain why gravity is so weak compared to, remember we talked about that specifically with electromagnetic. Well, electromagnetic force is weak compared to these 2 forces. I'm not sure about this one actually offhand, but strong force for sure. Yeah, so, I guess I've been talking about this anyway. So yeah, the strong force causes protons to stay together, and it's the strongest. We talked about electromagnetic force. Then there's this weak force, which causes decay. So again, they think that there's some interaction with the W or Z particle. It collides with a proton and causing that proton to become a neutron and the antimatter electron. And that's what causes decay. It's all because of, you know, these bosons bumping into the protons. I think that kind of makes sense, right? That one you can picture pretty easy. And then, like I say, gravity. I'm hoping to find it, but there's this thing called the Higgs, and I know that Brian Cox does a nice explanation of it in the video, but 1964. Oh, I thought it was 69, but so 64, he explained, you know, why do some particles have mass, like all the particles we can think of, except for the photon. And, you know, he predicted it, Peter Higgs predicted it way back then mathematically, and it was a real treat for him to get to be alive to say that they found it. And here's a little...
Let's cut to the chase. How does the Higgs field give particles mass? And to be clear, we're talking about the Higgs field and not the Higgs boson, which is merely an excitation left over after the process we're about to explain. But I digress. Back to mass. To begin, we need to know what we even mean by mass, so we'll head the other direction and talk about what it means to be massless. This may sound crazy, but the defining feature of any particle without mass is that it travels at the speed of light. In fact, if we're honest, it should really be called the speed of massless particles. But since the first massless particles we knew about were photons of light, the name has stuck. Anyway, the point is that all massless particles travel 300 million meters every second. The details of this are explained by special relativity, but simply put, it's physically impossible for a massless particle to not travel at 300 million meters per second. And so mass is just the property of not having to always travel at the speed of light. As a side effect, this also means not being able to travel at the speed of light, but the key is that particles with mass are lucky enough that they get to travel at any speed they want, as long as it's slower than light. The amount of mass something has just tells how hard it is for it to change from one of these speeds to another. Now, in part 1, we mentioned that if there were no Higgs field in the Standard Model, all particles should be massless and thus travel at the speed of light. But you and I and Swiss cheese clearly have mass, because we have the beautiful luxury of being able to sit still. So how does the Higgs field help us do that? Well, while massless particles can only travel at the speed of light, they are allowed to bounce off of things. Things like particles, which are really just excitations in a quantum field. For example, the electron field is more concentrated at certain places, called electrons, and everywhere else is empty space. But the Higgs field is unusual in that it has a high value everywhere. And to be clear, this high value is not the famous Higgs boson. That's an extra excitation in addition to this already elevated field. But because the Higgs field has this everywhere non-zero value, any particle that can interact with it is pretty much bouncing off of it all the time. And if a massless particle bounces back and forth, or since it's quantum mechanics, does both at the same time, then even though in between bounces it travels at the speed of light, when you add everything up, it looks like the particle is going slower than light, maybe even like it's not moving. And since only things with mass are allowed to not move, our massless particle now looks and acts like it has mass. Well done, Higgs. What's more, the Higgs field can even interact with its own excitations, which is to say, it can give mass to the Higgs boson too. Actually, the Higgs field likes to interact with itself so much more than with the lowly electrons and protons that make us up, that the Higgs boson has a great deal more mass. But we shouldn't complain, because even though the Higgs has given us a lot of trouble and only a little bit of mass, at least we have mass, which allows us the simple pleasure of not moving.
Again, pretty confusing. Feel free to watch the other ones as well, but the Brian Cox video, which is Crash Course, part 1 and part 2, well, he does a great explanation. Yeah, okay. So, fourth thought experiment is not a thought experiment, but one-page report describing what you see as the most important scientific problem facing humans. It doesn't have to be a physics problem, though it really will be. And I mean that because everything's physics, right? And so something that you know, you may or may not know much about, but I've hinted on is this Large Hadron Collider, this huge collider out in Europe. It's got thousands of physicists working there, and they're looking for things like, well, they were looking for the Higgs boson. They're looking for multiple different dimensions. You should spend a little time reading about it. But, you know, do you think that's the type of thing that humans should be spending our money on, or is there something more practical? And one of my favorite guys, Neil deGrasse Tyson, he's so pro science spending. You know, he might give you a different perspective, like the idea of spending, or ask Mr. Restall about Euclid and the penny. You know, the idea of research just for the sake of knowledge. And sometimes that's what happens out at the LHC. It's stuff that seems so not tangible, but there's a very strong argument for that. And then the other, the flip side of that argument is, more money into very practical things that are affecting society right now. Anyways, spend the time thinking about it. Give me 3 to 4 paragraphs on your thoughts. I really mostly just want to know your thoughts. You don't give me a bunch of research. I know the research. I know that part. I want to know what you're thinking, but you need to do some research to do a good job I want some educated thoughts, not just your jump on the spot conclusion. Okay. Anyway, that's the fourth, and then the fifth is just to make up your own. This is a thought experiment. This is different. This is obviously not a thought experiment. This is just think for a little while with a little bit of research. I don't want your research though. I just want your thoughts. Here, I want you to make up a thought experiment, something practical. Don't make it too crazy that there's no real good answer to, right? Make it something that's sort of real and practical, classical physics preferably, please, and make a thought experiment, classical physics, and then give me your answer to it. But yeah, don't look one up. I know all the standard ones, so I think I do anyway. So I want your own. Anyways, that's it. That's the unit. Good work.